Previously, when computing a basis for the space of k covariant alternating tensors, we have used the fact that the following pairing gives us delta ij. So why is that? Well, in general, how do we compute the value of a wedge product of one covectors? Now let's just look at generally, when these phi are linear functionals and ei are vectors in V, they don't need to be basis elements or anything. We want to compute what this is. Well, if we look at the definition of the wedge product closely, then this turns out to just be the determinant of the matrix with this entry. Some books actually use this as a definition of the determinant. So let's see why that is. Right, so observe that the left-hand side is just summation over the orbit of this tensor, adjusted by the sign of this sigma. So this part is equal to this part, right? And then we need to apply it to E1, Ek. But this action here, right, by definition, this is just this phi applied to a permutation of the Ei. And this pairing is by definition just this product. But look, this is just the definition of the determinant of this matrix. Remember how we get the terms of a determinant? In each column, we take one entry. And these entries have to lie in different rows. Then we multiply these entries together and then put a coefficient in front of it. The coefficient is the sign of the permutation corresponding to this order of this entry. This ordering of the Ei. And that's exactly this. This is one entry for each of the column, right? And then sigma 1 here is 2, right? Sigma 2 is going to be 1. And then we multiply with the sign. So we see that we can compute this using the determinant. And alternatively, this also gives a definition of the determinant. To compute the determinant of a matrix, say M, we can just put, instead of Ei here, we can put this to be the rows or the columns of M. And for this phi, we just take the coordinate functions, the dual basis. Because if we have a matrix, that means that we have specified some kind of coordinates, right? In that case, phi of Ej is just going to be the ith coefficient of this vector, the j column or the jth row. And so this matrix is actually just the original matrix M. By the way, in the special case when the Ei's are a basis of V and the Phi are the dual basis, i.e. the coordinate functions, then this matrix is just going to be the identity matrix and this determinant turns out to be 1. And from that, and this formula is not hard to show, that now if these Ei's are part of a basis, right, and Phi we're taking part of this dual basis, then this value is 1 if and only if the indices I and j match up. Alright, so that concludes our discussion about general tensors and exterior algebra. Now we want to look at the specific case of tensors that arise from manifolds. So let's do that in the next video.